But these are the basics for what we need to go forward. Any questions? Okay, next thing. So we need to understand a little bit better to go forward what probability distributions. Now, the sort of probability distribution that we're used to seeing, and for a moment I'm talking about probability distributions, I'm going to be talking about the picture, or in other words, the histogram. So what sort of picture of a distribution are we used to seeing? We're used to seeing the ones where we just draw the rectangle. So there's a couple different rectangles. And let's see. Okay. Sorry? Yes, we're going to get to that. All right. So for a moment, let's see. What I'm going to do is I want to... Is this the right thing? Yes. Okay. I would like to talk about this example. So perhaps this example looks familiar. It should. Okay. So I'm going to ask a bunch of questions so we start thinking about the right thing. Actually, I want to do something before I do this one. Okay. All right. So sorry, I want to come back to that. First, I want to talk about this. What does a probability distribution histogram look like for a continuous variable? So again, what we're used to seeing is something with a bunch of rectangles, right? So our first data value or data class, we draw a rectangle for that. Then for the next one, we draw a rectangle. Then for the next one, we draw a rectangle. So we usually wind up with a histogram that's got like 5, 6, 7 rectangles on it. But we can make that picture more precise. So for example, here's the age one. Yeah. There we go. That's the one I want. Okay. So here, what's our first data class? It goes from 10 up to 20. Next data class goes from 20 up to 30, from 30 up to 40. This is that example of ages that we talked about quite a lot. Okay. We can make this more precise. How can we do that? Well, instead of saying the first data class goes from 10 to 20, we can break that down even more. We can say, well, instead let's use data classes 10 to 15, then 15 to 20, 20 to 25, 25 to 30. And each one of those gets its own rectangle. Does that make sense? Okay. But we can be even more precise. So we can make the first data class from 10 to 11, then from 11 to 12, then from 12 to 13, from 13 to 14. And each one of those little classes gets its own rectangle. This is a process of becoming more and more and more precise. Remember, instead of just saying, and it makes sense to think about this in terms of ages, imagine instead of asking someone, how old are you? Oh, you're 17. You could say, well, 17 and what fraction? So you could measure someone as 17.9 years old or 17.823 years old. So you really can have values everywhere in between. So what does this do to the histogram? There we go. Okay. Well, we start out with a histogram that looks like this. with the fat rectangles that we're used to seeing. Next, we make our data classes smaller and therefore more precise. So we get a histogram with lots and lots and lots of skinny rectangles. Now, to get the picture to be what I want it to be, imagine instead of drawing a histogram, we draw a frequency polygon. So instead of drawing rectangles, we just draw a dot at the top of every rectangle. What then happens? As we make our rectangles skinnier and skinnier and skinnier, we get a whole bunch of dots that are closer and closer and closer together. Because instead of having, say for example, 7 classes with 7 rectangles, you have like 100 classes with 100 rectangles and 100 dots. The more you do this, the more the dots get bunched together, the more your picture looks like the last one, where it's just a bunch of dots. Now, if it helps to understand what this last picture represents, use your mind's eye to draw in lots and lots and lots and lots of skinny rectangles, where each dot on this graph represents the top of a rectangle from your histogram. Does that make any bit of sense? So, if nothing else, imagine that we take our original histogram with the rectangles and take a sander to it. And instead of having these blocky tops, we just smooth it out until it's this smooth coat. The bottom line is that each of these represents the same thing. It's just that one of them is blockier and the other one is smoother and, in a sense, more precise. Yeah? Absolutely. Yes. Absolutely. Okay. So the first thing I want to show you is that we're going to be looking at pictures or histograms that look like not these blocky rectangle tops, but look smooth. That's the first thing. The second thing I want to talk about is how can we figure out probabilities from this picture? Now to do that, first thing I'm going to do is go over here. So let's talk about the data class from 90 to 100. And if you remember, these represented ratings. Now, what's the probability that a rating is between 90 and 100? How'd you get 1 out of 9? How'd you get 1 out of 10? Okay. 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 Are all of them equally likely? You're partly right. Yeah. It's 3 out of something. 3 out of what? How do we know what the probability is for a rating being from 90 to 100?
3 out of 10?
Yes. So it would be, it's a 0. It's a 3. Right. So one way to do this is just to say, well, how handy we've got the actual chart with all the information here. So what's the probability of the class from 90 to 99?
9.
What's the probability? It's something out of something. That's what a probability is. Yes, it's 3 out of 8. How many values are in this class? 3. Out of how many total? 8.
Where did you get? I know 3 of the people. Where did you get 8?
What's 8? The total number. Altogether we have 8. Okay. Now if you actually take 3 divided by 8 and get it as a decimal, 0.375. Okay. So the probability of being in this data class is 3/8. I'll leave it as a fraction, it'll be easier to talk about. 3/8. What I want to convince you of is that we can also figure that out just from this information. How? How can we use that picture to figure out that the probability of getting a rating from 90 to 100 is 3/8? Just from this picture. Just from this picture, we can figure out the probability of a rating being from 90 to 100. Well, just looking at the picture, how many, well, we can break this down. How many ratings are from 50 to 60? Well, we don't know exactly, but we can say there's one box worth. So 1 unit. 1 unit of ratings were from 50 to 60. How many were from 70 to 80? 1 unit. How many were from 80 to 90?
3.
Why don't you just show the exact amount?
Because I'm making a point. Okay. So there are 3 units worth from 80 to 90. Now how many are there from 90 to 100? 3 units. So what's the probability of getting a rating between 90 and 100? 3 out of 8. So you can see it just from the picture. Now my point is not to make you do visual estimations and break this up into units. My point is the following thing. If you are looking at a histogram, you can find probabilities by looking for these quote-unquote units. But what do these units really represent? They represent area. They represent area. So I was calling it units to give you something visually to look at, but what I'm really talking about is area. Okay, so what we're really saying is that another way of saying the probability of having a rating from 90 to 100 is 3/8. We got that by looking at the total area of the entire histogram and saying how much of that area is between 90 and 100. It's 3/8 of the total area. So the probability is 3/8. So this is really important. One of the important things we're going to be doing going forward is looking at histograms like this, and we'll be asked questions about the probability. And finding the probability will be the same as finding the area. So probability and area in this representation is the same thing. Let me give you another context where this is true. So, here is a picture of a probability distribution of temperatures from 70 to 75 degrees. Now again, remember, it's represented by a smooth line, not a bunch of rectangles. Now, what is the probability that the temperature is between 70 and 72 degrees?
4.
Can the probability be 4?
No, 4 out of.
Oh.
3
Okay, now how'd you get 3 out of 5?
4 out of 8?
So the thing is, we get, yeah, go ahead, I mean. 4 out of 10. How'd you get 4 out of 10? You're exactly right. And it's easier, you can just say 2/5. And it's easier to understand it as 2/5. So Irene's exactly right. Let me now reinterpret for the whole class. From 70 to 72, so what we're interested in is how many, what's the probability that we're between 70 and 72. But like I said, we start thinking about we start thinking about these things. Probability is the same as area. So asking what's the probability that we're from 70 to 72 is the same as what's the area from 70 to 72. Now how can we represent that, or how can we see that? Oh. So what we're really asking for is, what's that area? Well, this should be pretty easy to figure out. Just looking at it, just looking at the picture, what's that area? Okay. Now when I say what's the area, it's what's the area relative to the whole thing. So, how can, right. So one easy way to deal with this is to say, well, let's look at the whole thing. What Irene did was she said, let me break this up into pieces. So the easiest way to break it up into pieces is just like this. So how many the way we've broken it up, how many total pieces are there? And how many do we want? 2. So the area is 2/5. So the probability is 2/5. And if you write that as a decimal, it's just 0.4.
Because I did that and then I crossed the line too.
Oh, okay.
I thought it was like 4 little boxes.
Oh. You could do that. You could do that, but it's just only thinking for all the stuff that we're going to do, it's helpful to think only using vertical lines. So get used to thinking of it in that way. Okay. So does this make a little bit of more sense? Okay. Let's do another example. Okay. And let me also remind you, we should think of the total area of this is what? Well, area is the same as probability. What is our total probability always? Total probability is always 1. So that's the same as saying the total area is 1. Okay. Next one. Same thing, but same picture, new question. What's the probability that the temperature is between 71 and 74? Okay. So if we're looking for a probability, what's the first thing that we should do? What's the first thing that we should do on the picture?
3 out of
Yes. We're looking for the area. So before we find the area, we have to say which area it is that we're trying to find. So which area are we trying to find? From 71 to 74. So the area that we're trying to find is this area. Now from looking at that, can you see what that area is? It's clearly 3 out of 5. So that's the answer.
Which is also 1.
3 over 5?
No, didn't you say like...
Oh, the total area is 1.
Oh, okay.
But what the area of this is 3 over 5, which is also 0.6. So now I just want to write this down to make sure that we continue to be familiar with the notation. So how can we write down probability that the temperature is between 71 and 74? What's the first thing I write down? P. Yes. Okay. So we're looking for P. Right. And remember, this is a between, so it's 71 less than X less than 74. And we just decided this is equal to 3/5, which is the same as 0.6. Now, I started off with this distribution, which is a very, very simple shape. What shape is this? This is a rectangle. So when I draw for you a rectangle and I say find the area, it's very easy. We know how to find areas regarding a rectangle. Now, by the way, when your distribution is in the shape of a rectangle, that is called the uniform distribution. Uniform meaning same. Okay. Now, in real life, you almost never ever have a uniform distribution. However, I started with that one so that you could get an easy, comfortable look at thinking of areas. It turns out that we're going to have to deal with distributions that look more complicated and say, how do we find the area of this complicated looking distribution? And that's the thing that we're going to talk about next. So far, does anyone have any questions?